Um, Welcome. Just before starting off, I'm sure everyone is familiar with fight has been long going on between Apple and FBI. FBI is public order Apple to create a spare encryption key and ship upcoming iOS with it so they can decrypt every iOS device if they need to. Well, this order publicly opposed by researchers, academicians, and by everyone who has reasonable knowledge in cryptography and security overall. And it seems Apple won this battle by for now. While all this happening, we were missing a tiny detail behind the scenes. Have you ever wondered why such thing never happened to GSM companies? Why they have never been neither object or the subject of the such battle? Well, I don't know, and I don't have answers to this question, but I hope you will be able to figure it out on your own today after this talk. So welcome again, my name is Omer. Thank you for coming and joining us here in beautiful Miami Beach. Today I'm going to present you an offensive GSM network security research related to the full chain of origin investigation and some of the vulnerabilities discovered along the way. So briefly about myself, I'm a CS major. I specialized in quantum cryptography and artificial intelligence during my studies. I'm currently working for KPN Telco in the Netherlands. And I used to work for companies like IBM ISS and Verizon. I perform red team assessments on my day-to-day work. And I spend my leisure time in malware analysis and rootkit development. Our agenda will look like this. We will briefly take a look on GSM network architecture and its network protocols that are highly being targeted, such as GRX, IPX network, and the SS7 protocol. And then we will discuss practical attack scenarios we successfully exploited during this research. Before switching to the regime, delving into its capabilities, we will briefly discuss how our approach looked like and what we aimed at. And afterwards, we will take a look on the region sample analysis components and how such tool could be used in an offensive GSM hacking. And finally, I will present you some demos, how the techniques employed by the region could be dynamically be analyzed, through instrumentation could be implemented, by a high-level programming language such as C++, Win API, Win DDK libraries. This is my team. We are based in Amsterdam. We are high almost every day, smoking weed, visiting beautiful ladies in the red light district. This is what we do almost every day, while our manager thinks that we are working. Motivations. Our fundamental inspiration was to understand the region type of incidents, attack surfaces of GSM, outer GSM and the inner GSM network. Governments not only hacking their own citizens, but they spy on each other by covert hacking operations with tools like region and stealth malwares. Surveillance programs reach at a crazy level. Recent leaks confirms that telecom operators are the victims or the contributors of such programs. I think it wouldn't be wrong to refer 2015 as the year of backdoors, as many of them have been discovered in the popular products. Once region hacking campaign revealed, pretty much each and every telecommunication company in Europe got paranoid about it and tried to make sure that they haven't been affected by the same attack. Rootkits require a lot to learn about operating system internals, kernel working principles, and computer architecture. So the GSM network architecture is really complex. However, let us try to break it into following core elements. So the outer GSM, in other words, signaling units, radio stations are base transceiver station, base station controller. Then there are inner GSM network components from a security standpoint. The important ones are mobile switching center. The mobile switching center is a digital ISDN switch that sets up connections to the other mobile switching centers and to the base station controllers. The mobile switching centers mostly associated with communication switching functions such as call setup, release, and routing, and some other host functions such as routing of SMS messages, conference calls, fax, and service billing, as well as interfacing with other networks. Equipment Identity Register. The Equipment Identity Register is a database that stores international mobile equipment identities, as known as IMEIs, of the phones, all that mobile stations in the network. The Equipment Identity Register provides security features such as blocking calls from handsets that have been stolen. Home Location Register is the central database for all users to register to the GSM network. It stores static information about the subscribers, such as the international mobile subscriber identity, subscribed mobile services, and a key for authenticating the subscriber. The HLR also stores dynamic subscriber information, for instance, current location of the mobile subscriber. Authentication Center works in conjunction with HLR. This database contains the algorithms for authenticating subscribers to the subscribers and the necessary keys for encryption to safeguard user input for the authentication. And then lastly, Visitor Location Register. The Visitor Location Register is a distributed database that temporarily stores information about the mobile station that are active in the geographic area for which the visitor location is responsible for. When a new subscriber roams into a location area, the visitor location register is responsible for copying subscriber information from the subscribers home location register to its local database. We can analyze GSM segments into two categories: base station subsystem and network switching subsystem. Base station subsystem is where signaling occurs, and base transceiver station and the base station controllers are hosted. On the other hand, network switching subsystem is the heart of GSM network, where the management databases such as HLR, VLR, Equipment Identity Register are hosted. These two interfaces communicate through SS7 protocol. Communication originating from a base station subsystem might traverse multiple mobile switching centers, but it must reach to the gateway switching center. Different signaling protocols are used on interfaces. Some network and switching subsystem interfaces involve only controlling signal protocols with no traffic. For example, no traffic is generated on the interfaces between GMSC, HLR, VLR. Instead, these interfaces carry only signaling using mobile application part of the SS7 protocol. Now you may ask, well, Omer, how these all are related to our research. One of the most interesting details of Regin campaign, it didn't target your bitcoins or bank account like most banking trojans or ransomwares do. It also didn't target your intellectual property or company secrets like most APTs originating from China or Russia do. Also, it didn't target your phones like NSA does. It rather specifically targeted communication between BTS and the station controller, the radio station controllers. Well, this tells something interesting, especially the attack targeted non-Western countries. This suggests military-related specific strategic missions are targeted. Wouldn't it be nice to be able to cut off all the communication means in a country that you are in war with? So we didn't know who would be dealing with, whether organizations like GCHQ, NSA, or offensive security companies like Immunity. We knew it wouldn't be easy, but we had a great aspiration from North Korea to bring them to their knees. In order to determine potential attack scenarios, we decided to perform a large-scale service enumeration from the base stations. We have intercepted communications between BSS, MSC, BTS, and base station controllers. So we greatly utilized Michael Oldman's passive network tapping utility in our research. We tried to collect as much information as possible from different endpoints of the switching centers, station controller, and any type of communications means in between. It also included the possible management services that were reachable from the network switches within the base stations. The information gathering phase also included station controller traffic and management of stations, radio stations, as Regin did on the attacked GSM networks. Our approach pretty much looked like as an outsider from a radio base station attacking through inner GSM network. Since base stations are one of the most other GSM network components, we wanted to see whether it is possible to attack other inner components which store juice information, such as equipment identity register, switching controller, home location register, and visitor location register. Well, the engagement revealed a number of terrible control check failures and issues. For instance, absence of physical intrusion detection devices, signaling intrusion, whether to detect wiretapping happens, did not exist, and devices could be altered and could be changed. Most GSM companies don't even take into consideration that could happen. Well, another issue was station power went off more than 20-30 minutes for that region when we plugged on and off cables for the interception, but the technicians couldn't notice it. and nobody came to check what was going on. Vulnerable services were running and accessible from base stations and open switch ports, reachable management interfaces with default passwords, and public and private keys in user directories. The absence of tamper resistance and unauthorized access protection. Well, the network tapping shouldn't have been possible otherwise. Improper network segmentation. Inner non-routable segments of the telecommunication are accessible. In other words, an employee's office computer was reachable from the radio tower. Core GPRS network and network subsystem were reachable and are running some of the vulnerable and exploitable services. If you ever perform a similar assessment, you would be surprised where you can reach within GSM network from the radio stations, especially if the segmentations are not correctly implemented. So let's take a look on the network components and protocols that could be targeted locally and remotely. GPRS roaming exchange acts as a hub for GPRS connection for roaming users, removing the need of dedicated link between each GSM service provider. In other words, your local GSM provider abroad, and its network consists of peering interconnects of the other GSM providers. The main GRX gateways are located for Europe in Amsterdam and for Asia in Singapore. IPX simply moves everything to the IP while introducing end-to-end model security and quality of service. Again, from a security perspective, both protocols have subtle issues, trust-based leased lines, failure of one, or malicious activity in one node would affect multiple of them. When Regin hit the Belgacom, a Belgium-based GRX operator, it later been revealed that the goal of the Regin operation was to enable network exploitation, ability to man-in-the-middle victims that use roaming. Let's take a brief look on how tunneling works on GRX networks. GPRS tunneling protocol is a group of IP-based communication protocols used to carry general packet radio service within GSM, UMTS, and LTE networks. GTP can be decomposed into separate protocols, GTPC, GTPU, and GTP prime. GTPC is used within GPRX core network for signaling between gateway support nodes, known as GGSM, and serving GPRS support nodes, known as SGSM. And GTPU is used for carrying user data within GPRS core network and between the radio access network and the GSM core network. GTP prime uses the same message structure as GTPC and GTPU, but it is largely a separate protocol. And GTP can be used over UDP or TCP, but UDP is either mandatory or recommended. So one of the most important features of GTP tunnel is that DNS on your GRX and IPX used for resolving APNs to set up GTP tunnel. An access point name, APN, is the name of the gateway between GPRS, 3G and 4G network and other computer network, and frequent access to the access node to the public internet. So how does a SGSN knows which particular GGSN gateway to connect to? So when a supporting node, SGSN wants to connect a subscriber to APN, it performs a DNS lookup on the APN name. This query is sent to a special DNS infrastructure called GN DNS. The IP addresses returned by the GN DNS is the destination addresses of the nearest serving gateway node, GGSN. And note that in order to scale network and provide geo-redundancy, that GN DNS may return different results depending on the source IP of the SGSN. In other words, completely trust-based. In the following network capture, from an attacker perspective, standard GTP packet transmits a lot of critical and useful information, such as IMSI, subscriber address details, subscriber network, and the tunnel endpoints. GTP protocol is really problematic. When the GTPC create context request comes from the unauthenticated SGSN to the GGSN, there's a bit says, it is cool, I have checked with your HLR, user database, and he said that it was cool to connect. It also being widely exposed to the DDoS attacks. Additionally, GGSN could be listed on databases like Shodan and etc. It's also important to mark that it is not necessary to have access to the GSM network in order to reach GGSNs. Meanwhile, GSM operators are freaking out about nation-state attacks. There are no words for this. I'm not sure whether 90s style of security issues are intentional or unintentional. Let's take a look on issues related to the SS7 protocol. SS7 is a common channel signaling system that transports SS7 messages over an SS7 network, which is developed 3 decades ago and wasn't introduced with security features back then. And then there is SIGTRAN. SIGTRAN is a set of protocols and extension of SS7, protocol that transport SS7 messages over IP network. Despite the ominous sounding name, SS7 is really just a bunch of network protocols used by most telecommunication operators throughout the world to talk to each other. SS7 handles all the basic routing and connecting functions that happen behind the scenes. When you send a message or make a call, SS7 is also what reconnects you to your carrier's network, and when you move between cell towers and passes the roaming fees back to your home network when you travel abroad. SS7 introduces procedures for user identification, routing, billing, and call management. SS7 consists of following parts: message transfer parts, NTP1, NTP2, NTP3, signaling connection control part, SCCP, transaction capabilities application, TCAP, telephone user part, TUP, ISDN user part, ISDN. The combination of the MTP and the SCCP is called the Network Service Part, NSP. SCCP provides a more flexible means of routing and provides mechanism to transfer data over SS7 network, and it provides database-driven application management functions. For instance, in your cellular network, SCCP transfer queries and responses between visitor location register and home location register databases. There are various ready-to-use tools available for SS7 experimentation on the internet. As a part of region malware analysis, as a part of region malware attack surface analysis, we perform a network traffic capture over SS7 protocol. The experimentation revealed that it is possible to exfiltrate many, so to say, juicy information such as caller node, calling node, information related to their call, such as call duration, call start and end times, and the call status. Let's browse through some of the attack scenarios over SS7 protocol. When a subscriber registers a switch, the subscriber profile is copied from HLR to the visitor location database. Assuming that an attacker managed to make changes in the visitor location register, he can change parameters and fake subscriber info so that victim can be redirected to a conference call so attacker can listen in. By introducing a decoy visitor location register unit, the SS7 network, an attacker can intercept SMS messages, send or drop confirmation that the message was received by the recipient. If victim use mobile banking or any other services that use one-time SMS pad, then the attacker can recover or steal these passwords to make money transfer or take control over these accounts. Furthermore, following attack scenarios are also possible by manipulating VLR, HLR units within the SS7 network, interception of SMS messages, interception of outgoing calls, redirection of incoming or outgoing calls, making changes in subscriber bill and balance. Well, you may say JSON providers should be able to do such things in their own network. You can also reconcile the fact that there are IMSI catchers, FATMO cells, and even completely trust a JSON provider in Iran or in Russia while you are roaming. But what if I tell you where you think your phone connects is not a JSON provider? Or in simpler words, you connect to the evil JSON provider without even noticing it. This is a company called Circles Bulgaria in Bulgaria, Eastern Europe, quote-unquote global innovator in wiretapping, offers enterprise-level wiretapping services by using SS7 network, and this has been recently disclosed. This company actually listed itself as a virtual operator to intercept encryption keys from the SS7 interoperator network in such a way, offering a real-time interception of calls and internet traffic, which until recently was considered impossible without the consent or cooperation with mobile operator that holds keys for encryption, session encryption keys. Their enterprise website is still up, and by their own words, it is not about who has got the most ballots, but it is about who controls the information. This is another interesting attack technique used by social engineering. Some of the telecommunication companies in Eastern Europe are targeted. Most operators have wholesale department or subsidiary, rents out access to the third parties and various service providers. The European Union, in fact, requires operators to provide such access in order to encourage competition in the mobile services market. Attackers simply impersonating telecommunication companies to sell or contract lease lines, and they were succeeded in this case. Well, I can't personally imagine anything worse than my lease line being sold to a group company as a legitimate GSM company worker. In cooperation with Nokia researchers, we have discovered that it is possible to unblock stolen cell phones by exploiting a trust relationship between IMEI and IMSI for equipment identity register access. The message application part is one of the applications of SS7 protocol. It is mainly responsible for mobility management and does additional services, equipment identity register, home location register, and visitor location register. Whether your phone is allowed to work in a GSM network, checked by map check IMEI message against the records stored in the equipment identity register database. Equipment identity register database simply checks whether switching controller returns 0 in map check IMEI, then treats phone as if it is whitelisted. Depending on this, switching controller takes the appropriate decision about the registration of the mobile device. Now, let's assume that an attacker has stolen a phone and that's blocked in the GSM network. He doesn't even need a SIM. It is sufficient to have just IMSI. The IMSI can be obtained by active attacks like using IMSI catchers, while it is also in use or using map send IMSI command within the GSM network inside. But there is a problem. Equipment identity register exploit the underlying mechanism as switching controller sends IMEI along with the IMSI during map check IMEI reply. The relationship between those two can be leveraged for unblocking a mobile device from the stolen list in the database. In such case, initially the IMEI is checked to know list it belongs to. If it is found on the blacklist, an additional check of IMSI is made. If there is a match between IMSI provisioned with IMEI in the equipment identity register database with the IMSI found in the map check IMEI message, then this will override the blacklist condition. Well, some people would probably argue this is a sensible feature if a phone accidentally blacklisted. Oh well, what GSM companies should do then, access control for switching on IMEI validation, logging of activation of the validation feature, filtering on map level of the check IMEI request is coming from a non-internal source, such like HLR, MSC, switching controller. If SS7 is run over IP, SIG-TRAN, then the usage of IPsec should be considered. According to the NDS and IP security standards, but most GSM companies don't follow it. An interesting mail disclosed on WikiLeaks between hacking team and one of their customers. Some of you may know hacking team was an Italy-based security company which used to sell exploit and surveillance tools to dictatorial regimes and countries. One of their customers was interested in location tracking via exploitation of SS7 protocol. This is technically correct. It is possible to locate someone by exploitation of SS7 protocol. Our recent research revealed that it is possible to locate someone's regional and as well as geo-specific location by exploiting a trust relationship in diameter protocol. We haven't released the article yet, but the technical details will be made available after Infiltrate.com. Many operators deploy diameter edge agents on the edge of their networks. Which is then only point of contact into and out of the operator network on the diameter application level. If an attacker connected to the IPX, then he can send messages to other partners connected to the network. First off, with some existing research, first location tracking attack has been disclosed on CCC conference in 2008. This attack type was simply abusing IPX service hubs. More specifically, routing process in the SMS. Send routing information for SM, message to pause, as a SMS center switch. By sending victim's mobile number, an attacker can obtain the subscriber identity and the mobile searching center of that is currently serving to the mobile of the victim. Another attack was disclosed in 2014 by Positive Technologies, outlining how to perform cell-level location tracking by abusing SS7 and MAP protocol. This went mostly unnoticed by the public, but when Analogy's location tracking attack was found and presented independently in December by Engel, the press picked it up and it was widely discussed. The attack happens in such a way that operator network internal anytime interrogation message returns to the cell ID. The interrogation message should not be responded on the roaming network. As we discussed, the HSS, HLR is the core databases which contains all the subscriber related key information such as location, contract type, and ISDM. The diameter agent address is considered to be public information and are visible via showdown since if it is deployed. All diameter messages to the operator will be sent through diameter agent, even if the final destination is home subscriber server. This would allow an attacker to obtain routing info request to the home location register database and phone number of the victim, where you could obtain subscriber identity, address of serving node, SGSN, and switching controller. Now an attacker posing as an IMS application server such as like SIP. He can send the user data request to the subscriber server address. By the way, user data request message doesn't require any IMSI to be present according to the standards. And home subscriber server responds with circuit switched location information, which will contain the location area ID, cell ID, where the mobile is currently located or where it was last located. Another way for an attacker to impersonate himself as a home subscriber server to send and insert data request with flag 3 to MME, Mobile Management Identity. Insert data request, flag 3 indicates evolved package system, EPS location information is requested. And management entities receives the message and assumes that it is coming from the home network subscriber server. It then sends requested information back. And the location information will pretty much look like this. EPS location in the answer contains the location area ID, which identifies a group of cells and the cell ID and the service area where the mobile is currently located, like 3 size location. What GSM companies should do in order to prevent such abuse, to use IPsec following 3GPP to ensure end of the tunnel have known identities, separate inbound and outbound SMS routing to prevent operator network sniffing, implement advanced access control list, whitelist, blacklist partner nodes, anti-spoofing, origin realm verification, implement cross-layer checking for messages routed over SS7 and diameter. I hope it is clear to everyone to remotely spying into a GSM company way easier than physically infiltrating into one of them. Especially time of the actions varies and targets are multiple. Because you would want to prefer a click of action over getting your agent on board, getting him hired by the company, and then risking his life or maybe getting him shooted. So this is where region comes into play. Region malware employs some of the common well-known rootkit techniques, but it also takes into another level with service-oriented architecture. Region is a very complex multi-platform rootkit framework that consisted of a dropper module, multi-stage user, and kernel level components. Each level seems to be responsible of decrypting and loading data modules into the memory and executing them. The most interesting feature of Regime platform was that it used orchestrator. That was very new to researchers until discovery. It can be thought as if RPC calls to specific kernel driver to enable and activate them, and then the payloads that utilize for actually performing malicious actions in the system. Well, the challenges and difficulties of the research, it was a multi-stage and encrypted framework structure. Modules invoked via service-oriented architecture structure by the framework. malware data are stored inside virtual file system, and also encryption was RC5. That wasn't commonly seen in malware implementation in that time. Research GSM network had no indication of compromise. So we came up with a solution that was the best way to start, to reverse encryption brain of the framework, orchestrator module, accompany them with memory dumps of the infected system, and instrument calls, and do static analysis in this way. This is done by one of my ex-colleagues, Mateo Kaczmarek, a peer of mine from Verizon. You could find the details in the following URL on the internet. No wonder IDA couldn't resolve the imports. This was only a memory dump. And the memory dump didn't have a proper header info. Instead, a marker later being discovered that it is used by region to determine its components. Analysis of the dump and the string hints out that it is likely a DLL file, which also later confirmed by the reports of the antivirus firms. Since orchestrator module, one of the region since orchestrator module of region was sort of crucial, we followed such a solution to reproduce valid DLL from the dump, fixing of DLL file, determining it is section headers and locations, and preparing and fixing the entry point of DLL file. And then both IDA and the debugger were happy, so this allowed us dynamic analysis. So I have a quick demo about this, how this works and how I implemented it. So when you open the dump file, it looks like this. There is no PE headers and the detail information. If you go through the dump file, this is an interesting tag for tagging your nodes in the command and control communication. And then there is DLL and the imports of Win API calls. So it was clear that this is a DLL or executable belong to the Windows platform. So when you align sections, import headers, it should look like this. IDA should be able to resolve the imports and API calls correctly. And then you can continue with dynamic and static analysis. And then this part is belong to the one of the dispatcher module, belong to the network module. What Reginist simply does is this DLL file, create an instance of Regin, because it uses object-oriented and RPC calls, so it creates an instance of object every time it initiates a module. Here it pushes module ID and then an instance of Regin. And then actual initialization is done here. Here a handler created for the particular module. Regin has a lot of module. So these are like constants in the Regin module. And if you ever dealt with kernel drivers from the user land, this is how you do it. You create a handler and then manage your system drivers from user land. And the dispatcher for every and each module is the same. If you look at the shape and everything and the arguments, it works in the same way, just module ID and handler. So it checks and it activates in the command and control architecture. It also includes the master and slave nodes. There is a bug in this. Anyone have an idea what is this? What kind of a bug there is? No one? All right, I will tell you. So there is no signature checking in this DLL file. So simply, if you find out that there is constants are being pushed to the DLL file, that determines and enables master and slave node and their TCP and UDP communication. So if you had this region module and dump on time, if you did the instrumentation, you could simply take over entire and command and control botnet that time. I discovered this quite after all these revealed, so I was banging my head why I couldn't find it when it was active. So this is the UDP communication module. This works in the same way. So I created an exe file using C++. It simply takes a handler and module ID and then sends this information queries through DLL. And then return back the information and activates DLL, the drivers in your system that is active in your file system. This is how my wrapper works. It simply initiates orchestrator, loads into memory. It is display DLL, as you can see in Process Explorer, and then invokes some hooks and pipes. My implementation a little bit has restrictions to prevent this bug in the DLL file, so I separated slave and master node in the implementation in exe file. So I didn't implement all the hooks, all the functions, all the modules, and I had only few of drivers, so I instrumented some of them, and I will show you how these can be dynamically invoked and can be worked on system. This is the virtual file system, default virtual file of the region. This is the location. So region infection uses this virtual file system in the Windows directory. If you can click on this, it is encrypted file system. And as you can see in the demo, this is actually used by my dispatcher that I created for the analysis. So region has a lot of modules like creating pipes, creating virtual file system nodes, and also creating TCP and UDP communication lines. And this is the network TCP module. So I had the real infection of the infected drivers. So it also contained the command and control IP addresses. Here is the first column indicates the TCP module of the region, and then IP addresses and the communication line. Here is this simple Python code to show you that this is an IP that belongs to a command and control server. You could probably see, you could have seen these antivirus reports as well. So logging feature, region also has this logging feature. Encrypted virtual file system is used for network traffic capturing. And it has a lot of modules, and any researcher has got all the modules. So you can, if you have some modules, you can drop me a line and we can take a look at it. It's very easy to invoke and get it running in such way, just doing instrumentation and through the orchestrator. So a little bit about region and its structure quickly. Stage 1, 2, 3 are the platforms solely responsible of encryption and decryption. It didn't do much on the system. Stage 1 is simply prepares execution of the stage 2, which is developed as a kernel driver module. And in this snippet, stage 1 is simply uses kernel level calls to allocate memory memory pool for stage 2, and consequently it makes sense since preceding module was a kernel driver. Stage 2 has configuration block, contains names of the two system directories, and let's hold the encrypted third stage and the extended attributes. So if the third stage sends signals, stage can delay the startup code of regime. The second stage also creates a marker that can be used to identify infected machine. It simply cleans the previous stage and creates the encrypted file system that's used for kernel level payloads. Stage 3 is kernel driver manager, and stage 4 is the brain of the region framework that is orchestrator responsible of loading kernel modules. Key stack attack process an interesting being API call. That routine attaches current thread to the address space of target process. Since our goal was to reproduce and simulate region functionalities and instrument payloads, I created a simple routine that simply attaches a thread to an application and intercepts system calls and changes in a way we wish. This is very simple code. Simply, the code snippet shows how to obtain, process, and one log of a running process, and then obtain the base address of the modules, and how to attach a thread to that process. This may not be very concrete comparison among the Ouroboros regime Dugu2. Dugu2 seems to be most complex rootkit until now, and also modules and approach to how to operate malicious actions on the system changed over the time. For instance, Ouroboros was bypassing patch cards back in the past, but Regime and Dugu2 were using stolen or legitimate certificates. In order to simulate regime behavior, I created a small framework consisting of two modules, kernel and user level module, and it simulates orchestrator behavior that is implemented by a region platform. The features of the simulator includes covered data exfiltration run as a thread on the legitimate application, address space and totally invisible to the users. Orchestrator simulator also implements partial RPC calls, monitoring of file system registry, network call hooking, and backdoor and key-logging module. So, quick demo. This is a kernel and user level module that I created as a small framework. What it does is simply creates a file system driver on the system, and then the executable actually does the instrumentation and send calls to the kernel driver. For the sake of simplicity, I hardcoded some addresses to run executable. So I simply run this batch file to initiate driver and then execute the user part of the driver, the rootkit actually. And it initializes and installs hooks on the system. One of the hooks is hiding file on the file system. So if you wanted to delete a file, it will prevent you from doing it. But the file is actually there. There are also registry hooks so that I prevent a user from deleting the kernel module on the system. So I removed the connect to my node. So this is a little bit different than what Regents does in an architectural way, but it rather connects to the slave on the open port and then provides some basic malicious options that can be extended, but for the demo I kept it small. For instance, you can run a process on the system, open files, lock the system, and encrypt entire system. So these are the dangerous malicious actions that this framework can invoke on the infected machine. It overrides the MBR section, and then the system will totally be corrupted. So as you can see, there is no operating system on the system, and it is destroyed. Already. So that was all. Thank you very much.
All right, so normally we would do questions, but we are predictably running late. So we're just gonna have to ask you questions during dinner tonight over a cocktail, which seems better anyway. I saw a lot of feature requests for Regen 2.0. and I look forward to those being used in the future. So next up, Android excitement. Where is he? Is he running around? Come up, put computer on. I think it would be ironic if all Dutch operations in England now use Regen using the new framework. Or just cool, it'd be cool.